In this short video, we're going to introduce double integrals with the simplest case, which is a double integral over a rectangular region. And before we talk about double integral, let's do a quick review about integrals that we learned in Calculus 1. Our challenge there started with trying to find the area under a curve, that is the area between a curve and the x-axis, over a closed interval. And the way we did that is that we divided the closed interval into n subintervals of equal length, and then we tried to approximate the area contained above each subinterval by using a rectangle. So the base of the rectangle was the width of the subinterval, that was our delta x, and the height was chosen as a function value at some sample value within each interval. Now that sample value could have been the left endpoint of the interval, or the right endpoint, or just some random number in the middle. But that would give us the function value at that point, would give us the height of the rectangle. And we would use the sum of the area of the rectangles as an approximation of the area under the curve. And to get a better approximation, we would just simply use more rectangles. And to get our best approximation, we would let the number of rectangles go to infinity, and that was our definition of the definite integral. Well, we're going to do something similar with surfaces. We'd like to be able to calculate the volume under a portion of a surface. And what that means is we'd like to know the volume between the surface and the xy plane. And again, in the simplest case, we're going to choose the region to be just a rectangle. So we have an interval on the x-axis, a comma b, and then we have an interval on the y-axis, c comma d, and that rectangle then is our base, and we're trying to calculate then what is the volume above that, between that rectangle and the surface above it. So we're going to proceed in a very similar way as we did in Calculus 1. What we're going to do is we're going to break up a comma b into n subintervals. We'll break up c comma d on the y-axis into m subintervals. And the n does not have to be the same as the m. But we're going to have then a mesh, and what we're going to do is to be able to calculate the volume above each of these little rectangles, these mesh cells, is we will choose some point, a sample point in each of these cells, each of these little rectangles, and the function value at that sample point we're going to take to be the height of a box. And then we're going to add up the volume of each of the boxes, and that'll be an estimate for the volume. So our box is going to have a base of delta x by delta y, that's the area of the rectangle, and the height is the function value at that sample point. And so if I just multiply those together, I'll get the volume of that box. And if I add up all of those boxes, now it's going to be a double sum because I have to add across the rows and the columns. That'll give me an approximation for the volume. And if I wanted to get a better approximation, well, I would take more boxes. And if I want to get the best approximation, I'll have to let the number of boxes go to infinity. And that limit of that double sum is our definition of the double integral over that rectangle. Now, we're looking at an example where the function values were all positive. They were all above the xy plane. And in that case, it does represent a volume. But very similar to what happens in one variable calculus, in general, the double integral represents a signed volume. In other words, it could be negative, positive, or zero, and geometrically it represents the volume of the portion of the surface which is above the xy plane minus the volume which is below the xy plane. So how do we evaluate these double integrals? Well, what we do is we write them as two regular integrals iterated. So one after the other. We have or nested maybe is a better word, because one is on the inside and one is on the outside. So we're going to evaluate the inner integral first. We always work from the inside out. And here the inner integral, we can see from the differential dx that we would need to take the partial antiderivative with respect to x. So we would treat y as if it were a constant and take the antiderivative with respect to x. After we evaluate that, we are not going to get a number usually. What we will get is a function of y only. But then once we have a function of y only, well, we'll be able to see that we just have a regular integral at that point. But we want to emphasize that how did we know that we're going to anti-differentiate with respect to x? It is the differential. And then when we set these up, we got to be sure that our differential is going to match the bounds. So these must be expressions for x. They don't necessarily have to be numbers, but they should be expressions for, x equaling something. So x equals a, x equals b, or later it'll be x equals some expression, or x equals a different expression. So again, once we've finished evaluating the inner integral, we will have a formula containing y only, and then we just evaluate the outer integral. And again, when we're setting this up, we want to make sure that the differential, the variable for the differential, matches the outer bounds. And the outer bounds have to be numbers. And in this case, they would have to be y values. Okay, so let's look at an example of an iterated integral. We're going to evaluate the double integral over the surface x secant squared of y, and the region is the rectangle where x varies from 0 to 2 and y varies from 0 to pi over 4. So that's our integrand. We're going to evaluate this in the order dx, dy. So I can see that my bounds here on my inner integral, which is the x integral, are 0 and 2, which correspond to my x values. The outer integral is with respect to y, and the bounds on the outer integral are y values. So I need to find the partial antiderivative of the inside. So normally we don't do all this writing, but since this is our first example, let's actually pull that inner integral out. And since y is being treated as a constant, then secant squared of y is also a constant. We can actually pull that out in front. And then I'm left with simply finding the antiderivative of x, which we all know is 1/2 x squared. And I can evaluate that between 0 and 2, and I'll get 2 secant squared y as the value of the inner integral. So again, I wind up with a formula that has only y in it. So I'm still left with evaluating the outer integral, but that's just an integral of a single variable, something that we worked with throughout Calculus 1 and Calculus 2. And in this case, the antiderivative of secant squared y is just tangent of y. And when I evaluate that from 0 to pi over 4, I get 2. Let's do another example. Here I have y times e to the power of 2x minus y as my integrand. And my region goes again, x goes from 0 to 2, and y goes from 0 to 1. So let's see if I can evaluate the inner integral. I'm taking the partial antiderivative with respect to x, but I see that I can first pull out the y, the multiplicative value of y, because that I'm treating as a constant, and constants, multiplicative constants, can be taken outside the integral. I can't do anything with the y that is inside the exponent, that is trapped inside the input to the function of the exponential. So that I'm just going to have to work with, but remember, I'm treating it as a constant. Now to find the antiderivative, 2x minus y is a function of x, and so I'm going to have to make a u substitution here. So I'm going to set u to be the entire exponent, 2x minus y. Du is just going to be 2 dx, because remember, I treat y as a constant. And then making my u substitution then, I'm not going to change the bounds of integration. I could do that if I wanted to. That's another way of performing the u substitution. But for the moment, I'm just going to use the u substitution to help me find the antiderivative. Once I find the antiderivative, I will replace u with its original value, 2x minus y, to perform the evaluation. So to remind myself that these numbers on the bounds represent x values, I actually wrote x equals 0 and x equals 2. So the antiderivative of e to the u is just e to the u. I still have now the 1/2 y, and I'm going to evaluate that between x equals 0 and x equals 2. Well, before I do that, I better replace the u with the original value, 2x minus y. Then perform the evaluation. So when I put in 2 in the place of x, I'll get 4 minus y. When I put 0 in the place of x, I'll just get e to the negative y power. Now with what's left over, I'm going to have to use a different technique of integration. I'm going to have to use integration by parts. Remember that has that formula u times v minus the integral of v du. So let's start with our u, and remember these are kind of the simplest integration by parts. We have a polynomial times a transcendental, like an exponential. The polynomial is always going to be u. Du in this case is half dy. Dv is going to be, I'm going to use the whole thing inside the brackets, and taking the antiderivative, remember I get this minus sign that comes out in front because of the minus on the y. We're taking antiderivative with respect to y, and so that's why the sign changes. Now I have negative e to the 4 minus y power plus e to the minus y. So then I'll take u times v minus integral v du. Now that's just a regular integral. I'm going to be just integrating, finding the antiderivative of e to the negative y minus e to the 4 minus y. I just changed the order there because it's nice to put the positive term first. And then evaluate that from 0 to 1. So if I did that correctly, and let me just double check while I'm here. That'll be e to the negative 1 plus e to the power of 3. And then subtract off e to the power of 0, or negative e to the power of 0. That would be negative 1. And then plus e to the power of 4. So it doesn't turn out to be a nice integer or anything like that, but it's certainly a valid value for our double integral. So now we've always been having the inner integral, an integral with respect to x, and the outer integral with respect to y. And the question is that a requirement? Is there an advantage to that? And the answer is no. And in fact, we have this theorem by Fubini, which tells us that when we're talking about a rectangular region, it really doesn't matter if you have a continuous function on the rectangular region. And in fact, you can even have a certain types of jump discontinuities or removable discontinuities, and this will still be true. So we can integrate then with either order. We can either have dx dy or dy dx. We just have to make sure that we line up our bounds with the appropriate order of integration. So let's look at an example that we've already found, and let's just change the order of integration. So instead of doing dx dy, which is we did in our first example, let's just switch the order of integration to dy dx. So now the bounds on the inner interval are y values, and the bounds on the outer integral are x values. We should get the same answer, which, if you remember, it should be 2. So let's evaluate the inner integral. X in this case would be considered a constant, so we'll go ahead and factor that out. Remember, the antiderivative of secant squared y was tangent of y, and evaluating that from 0 to pi over 4, you just get 1. So I'm just going to get 1x dx. Its antiderivative is half x squared. Evaluate that from 0 to 2, and sure enough, I get the same answer, 2. So let's work kind of in the opposite direction in this example. We're given a double integral over a rectangular region, and it represents a volume of a solid, and we're asked to sketch that solid. Well, let's look at the integrand. z equals 4 minus x minus 2y. So at this point in our journey through Calculus 3, we should recognize that that's the equation of a plane. And we can sketch the plane, or at least the form of the plane, by using its intercepts. So I'm just putting x and y equal to 0, and I get z equals 4. If I put y and z equal to 0, I'll get x equals 2. And if I put z and x equal to 0, I should get y equals 2. And I see that I have a bummer mistake there. So let's fix the intercept. We know that it should be 0, 2, 0 if it's a intercept on the y-axis. All right, but that's not the volume, because we're only interested in the portion of the solid under that plane, which is above the rectangle 0 to 1, 0 to 1. So x and y both go from 0 to 1. So I guess really it's a square. And so it's actually this portion here. So we have a square base, and then it goes up, and you have this kind of, well, it's not a parallelogram as the roof of this box right there. And let me make my correction again. All right, now let's calculate the volume of a solid. It's going to be enclosed by 2 plus x squared plus quantity y minus 2 squared, and this collection of planes. Now, the planes that define our x values, that's just going to give me the rectangle, right? Our rectangle along the x-axis goes from -1 to +1, along the y-axis from 0 to 4. What does this look like? Well, I did my best to try to sketch this. I know that this is going to be a paraboloid. It's actually going to be, this cross section is going to be a circle. It's going to lie 2 units above the point where y equals 2 along the y-axis. And then this is something new. We're not going to actually find the volume of the surface under the paraboloid. We're going to find the volume between the paraboloid and the plane z equals 1. So just like we had in Calculus 1, an upper curve and a lower curve, and we're trying to find the area between the curves, we can do the same thing with surfaces. We can find the area between the surface. So we have an upper surface, the paraboloid, and a lower surface, which is the plane, z equals 1. And the way we handle that is the same way we did with curves. We just take the top minus the bottom in the integrand. So that's my top surface minus the bottom surface. And again, the other planes here really just define the box here that I need to be calculating for the limits or the bounds of my integration. So x goes from -1 to +1, and y goes from 0 to 4. So let's just start by collecting the like terms in the integrand. We'll take the partial antiderivative with respect to x. And here, I'm adding y minus 2 quantity squared. That I treat as a constant. So just like the antiderivative of any constant would be that constant times x, I'm going to take that constant, y minus 2 squared, and multiply it times x to get the partial antiderivative with respect to x. Then evaluate that between -1 and 1. So remember, I'm just replacing the x values with 1. Subtract off the value when x equals -1. And so then I get a new expression with y only. And let me clean that up by collecting the like terms again. And now I need to find the partial, not the partial, it is the antiderivative. Y is the only variable. So I'll find the antiderivative of y minus 2 squared, which will be 1/3 y minus 2 cubed. Now, when I was first learning antiderivatives, I would want to make a u substitution here, but at this point I should say, well, if I make a u substitution, I can see that du is the same as dy, so I'll go ahead and just apply the power rule directly to the quantity y minus 2 squared. And now I got to evaluate that between 0 and 4. And if I did my arithmetic correctly, that gives me 64/3. At the end of Calculus 1, we learned how to find the average value of a function of one variable by taking its integral and dividing it by the length of the interval. We're going to do something similar here. We're going to find the average value of a function of two variables over a rectangular region. Actually, it doesn't have to be a rectangular region. Just over any region R is you find the double integral of the function over R and divide that by the area of the region R. So let's find the average value of f of x equals x squared y over the rectangle with the given vertices -1, 0, -1, 5, 1, 0, and 1, 5. So I can see that x goes from -1 to +1, and y goes from 0 to 5. So that's my rectangle. I'll go ahead and calculate the area of a rectangle. It's just length times width. From -1 to 1, that's a distance of 2. And from 0 to 5, that's a distance of 5. And so the area would be 10 units squared. So I'm just going to evaluate the double integral and divide that by 10. So evaluating the inner integral, take the antiderivative with respect to x. The y is a constant multiplier, so I just get 1/3 x cubed y. Evaluate that between -1 and 1, and I get 2/3 y, and take its antiderivative. That would give me 1/3 y squared, but I have to multiply times 1/10. That's how I get 1/30. Evaluate that between 0 and 5. That'll give me 25/30, which is simply 5/6. So that's our introduction to double integrals. In our next video, we're going to look at what if we have a region which is not a rectangle? How do we evaluate that type of integral?